All right, we're going to take a look here at the software, this example software. And I'm going to step through kind of what it does and kind of give you an idea how to use it so you can write your own application. So the first thing we're going to look at are the first two lines here. The include embed H, that comes with all programs to include the embed libraries. The include Chembox interface is to include the function declarations for all of the hardware drivers. The next two things I'm not going to look at right now. We're going to come back to those. The control loop timer and the current temperature variable. This is just an embed object. One of the nice objects they give you in the embed library. We'll come back to that. So in the main loop, one of the first things I do, you have to do is call init chembox. What that does is gets all the hardware set up, gets all the chips that are connected to the embed initialized. So the first thing I do is show you how to beep. The unit just beeps 6 times. I have a simple loop here, and you notice I call this function buzz, and I give it a time of 50 milliseconds. Now, one thing you should know about buzz is that the actual buzzing operation is done with a PWM output in the background. So once you call it, it immediately leaves. So if you wanted to beep in succession, it's not like buzz will wait for 50 milliseconds here. It immediately just starts the hardware and leaves. So for example, I wanted to beep 6 times. So, and I wanted to have like a 50% duty cycle on the beep. So what I do is I tell it to buzz for 50 milliseconds and then wait. Wait is an embed supplied function, and the wait function just sits here. It blocks everything in the foreground loop from happening. So it'll wait 100 milliseconds and then it'll loop. So what'll happen here is you essentially get buzzing for 50 milliseconds over that 100 milliseconds period. Give you an example. The next thing I do, there's a little smart switch on the little LCD on the front of the box. There's a function to set the backlight. You can actually change it in real time. It takes an RGB value where there's kind of 4 settings for RG and B, 0 through 3. Doing this turns it white. So the next thing I do is show you how to use the screen in case you want to put something on it. Now, a quick note about this. You don't really have to know a whole lot about how it works. It's a 64 pixel by 32 pixel screen, and you just draw into it. You can draw, lines, points, or put like little strings, little characters on it. But the thing to remember about all the graphics calls is that they're fully buffered. So whenever you do a draw, you're not actually drawing to the screen. You first draw to like a memory buffer, and then when that's all done, you dump it to the screen. And that kind of reduces flicker and makes it look smoother. So the general operation, anytime you want to put new information on the screen, is you call this full display buffer clear. So this clears out that back buffer. The next 4 things I do, I have a function called GFX draw line, and you can find that draw line in the Chembox interface. Oops. If I scroll way down here, I have the display buffer clear function. We can put a single dot. I can draw a horizontal line, a vertical line, an arbitrary line, like at an angle, a box, and I have some string functions, so to draw characters. So I draw some lines, and what I do is I use this macro. This is just a macro in C that's defined as, the number of pixels on the screen. So in the X direction it's 64, in the Y direction it's 32. After that, I show you how to draw a string. I put Rioux box at coordinate. The upper left corner of the string is at 6, 2, positions X6, Y of 2. And there's 2 kind of little character fonts. One is called 5 by 7 for a 5 pixel by 7 pixel, and the other one is 3 by 5. So I use the 5 by 7. Then I draw a little line below it. Then the other thing I show you is if you're used to any C programming, there's always this function called Printf that you can kind of draw formatted text, meaning you can kind of intersperse variables. Well, I have a function called GFX Printf. It kind of works like Printf, except you give it the back buffer, the coordinate, the font. Then after that, it takes arguments just like Printf would in C. So what I do is API version is just a string defined in the ChemBox interface H file. I'll show you, it's right here. It's a simple string. And %s is the replacement for a string. If you wanted a number, it's %d. It just kind of shows you if you want to print variables to the screen while it's running. Now the final call you do is, it's called this dump render context to physical screen. What this does is it kind of moves that back buffer and dumps to the screen. So the general order of operations is you clear the screen, you kind of draw to the, or I'm sorry, you clear the back buffer, you do all your drawing, and then you dump to the screen. All right. I'm going to come back to this control loop timer here in just 1 second. Just ignore this for a sec. So the next thing I have is what I call the main super loop. So a while one is just an infinite loop in C. So I have a bracket here, a curly brace here, I'm sorry, and a curly brace here. So it'll just loop through, this over and over again. So the function that does all that magical terminal stuff, the terminal commands, you just call with process terminal. So this function will, every time you call it, it checks the incoming USB to serial port, kind of decodes characters, and does any kind of callbacks to any of those library functions to kind of like read temperature or set, a solenoid or a heater. So this is, if you want that functionality, this has to be called in your main loop, and it has to be called often enough that it can kind of process data, because if your other functions hang up for too long, it'll kind of make it seem like the terminal's running slow because it needs some time too to execute. Now, to kind of show you an example, of how you would do a control loop like in C code, there's many different ways, but this is a 100 megahertz processor. So it's pretty fast for a microcontroller. It has lots of CPU time. So the worst thing you can absolutely do is have any function that just sits around and waits for something to happen. And so some control loops, for example, let's say we wanted to wait and execute something every quarter second, 250 milliseconds. The worst thing you could do is have a function that has the CPU sit there and wait, because it could be doing other things. So I show you an example how to get around that, because there's no operating system here. So whatever goes on this main loop is kind of it. So the embed libraries have this concept of called a timer. So if I go to the embed website, I'm going to go under handbook, and I'll scroll down, and we'll go to the library section here, and we'll go under timing. It's called a timer, and all the timer does, it starts a piece of hardware in the embed microcontroller that always just kind of counts up. Starts at 0 and goes up to like a 32-bit number. So once you create a timer object and start it, kind of in the background you have this little thing that's kind of ticking away. So the best way to think of it, it's a piece of hardware that once you start the timer, you can periodically read it to see how much time has elapsed. So I have some code here that I have put, it's commented out with the comments, so we'll look at it, is that I just use a timer object that every time I run through the main loop, I see if 250 milliseconds has expired. And if so, I do my control code, and if not, I leave the if statement and do something else. So to create a timer, I create it as a global variable. You just say timer is that's the object, and I gave it a name, control loop timer, and that creates a C++ object. Now I have a floating point variable called current temperature. We're going to use that later. What I do is, because it's C++, it's object-oriented, use the dot to invoke a method. So the first thing I do is call its reset function. It resets to 0. Then I say start to start the timer. So in the main loop, if this was uncommented out, what I do is imagine this loop is going around and around and spinning around. Well, every time it spins around, I simply ask the question, is the timer, and I can do this read milliseconds. Actually, I forgot the brackets here. Sorry, the parenthesis. If you call the read milliseconds method on this object, it just returns the current value of the timer in milliseconds. So what I do is I say if the current control loop timer dot read milliseconds is greater than or equal to 250, meaning 250 milliseconds has elapsed, it'll do whatever in this box. And if not, in this block, and if not, it'll just leave. Now this is a lot more efficient than, say, calling the wait function here, because the CPU just won't sit there and wait for it to happen. It'll go down here. If there was any functions down below here, to execute them, or else it'll loop up, check the terminal, see if there's any tasks to be done in the terminal. So in here, I just show you the first thing you got to do is reset the timer to start at 0, so it can count back up again. And then after that, I just call the read thermocouple function. In this case, I'm reading channel 0. I put it in a value. And I do a simple on-off like a thermostat. I say, is the current temperature less than 15.5 degrees C? If so, I call this enable heater function on channel 0. If not, I disable the heater. So it turns it on if it's less than this temperature, on if it's greater. And I mentioned in the header files that to keep in mind that all of these digital I/O that go to the heater and the solenoids are queued operations, meaning when you call this, it doesn't immediately execute. What it does is it kind of queues the operation up until you call this flush digital I/O. And the reason it does that is I had to put some shift registers on the board to kind of expand the I/O on the mbed because there wasn't enough. And so everything kind of gets queued up, then I shift it all out. So this just shows basically how you would enable the heater, enable and disable it and read a thermocouple channel. Now, all of the other functions, if you want to turn on a solenoid valve, disable one, it's all in here. And it's documented, so you know what it's all about. Now, other than that, that's really all there is. So just call this process terminal. You can put a control loop here and kind of come up with your own application. And that's kind of like a quick overview. So just start kind of playing with it. Be careful with the solid state relays, but I would just start playing with some code and experiment a little bit.